I really find it interesting to come towards the end of the day after I've seen all these presentations, starting with Ron this morning giving us the background that many of us have lived through the last 25 years, basically, and then followed by Jack about the evolving methodologies and the different documents and the available scientific data or test data. It's interesting to kind of connect all this. And I need to give you this comment because it's going to lead us to what I'm about to present. John Stewart about the characterization of the demand and the proper modeling of the input demand. And followed by Greg, what is the nitty-gritty areas of modeling, what it takes to model different systems, different components, what is the limited data, what is the backbones coming from, the probabilities of risk. It's very interesting how all this evolved to basically help us, as Greg put it properly in response and John repeated, we are all practicing in a standard of care that evolves at the time. And the best we can collect, that's why it takes a collective and a collaborative effort. You're going to see that very clearly in the presentation I'm about to make, because it was done most of the thinking in 2005 and 2006. Before, while many of the documents that were mentioned, and I'm showing similarly, they know to eliminate some, about when they were still in committee or in draft, and the collaborative nature of our profession and interest from research, academia into practice, ground motions, material science, how it all came together to help us, honestly, in the initial concept of this project. With that, I would like to, and you're going to see that many of the fundamentals that was presented in the last 6 or 8 hours basically remain the same, even when we change from concrete to steel. It's an interesting that the system that was needed and used for this project was basically a steel plate, all steel system. I want to get this going. Okay. The prior one is not closed. Here we go, thanks. The project I'm presenting to you this afternoon is about the Los Angeles Convention Center. It's a 55-story building, and the final system is really, that was used, is the end-stiffened steel plate. And really it came out of evolution of design, and I'll go through that quickly. What I'm not presenting you, the project description and how the site had complexity of an integrated site of multi-phase development, the architectural features that inspired the structural system, and how the structural system became a good fit, and that's going to lead to what is the structural concept. Then at that time, we needed a lot of research data that was not really codified, and I'm going to walk you through the process of how we took it from research to practice. I had to reduce this piece because there is so much background, but it's all published. Then how the performance-based design came to real help in a collaboration to allow different components, different approaches, things that were not necessarily codified, but they were in state of development. That led us to proper understanding of behavior and performance, as you've heard before, collaboration of a team, not just the peer review team, but beyond that, many researchers in this country and abroad that were working on specific components that were able to glean their knowledge, and construction highlights and goals achieved. It is a 55-story, it is about 665 feet tall. It's got multiple occupancies through the height, and it will show, and it's got very tapered, slender profile. This is what I was talking about, the phase construction that you see on the north side. We had to build a truck tunnel to feed into the development that's on the right side of the chart here. And that had to be done before us. When we were still working construction, we had to develop a retention system to hold the street, basically, which is Olympic Street. Similarly, on the south side, we had to build in an access and a fire lane to the Nokia center that's below us or south of us. So we're working in mostly an island. At the end, We only have shear walls or basement walls on the north side and the east side and the west side, but not on the east side or the south side, which caused a lot of peculiarity and phasing. The tower, as I said, I want to give it a quick glimpse. The tower has been in evolutions for probably 10 years for the convention center. Conceptually, it was always conceived to be concrete, and some schemes were concrete core and steel gravity framing, until the program developed further, and it dawned on us, why not a steel plate? And it was, you'll see it was a response to the program, and you see the program, I can get this, here we go. You see the program had special units, conventional small units, modules in the base, and then it had a pronounced cantilever to expand the floor plate, and then a sloping column system to basically enlarge the floor plate. It is also has some double-story heights. It's a response to program. It's not just aesthetics. And then you see it in the cross section. You basically have a tower, you have a pull deck over that extended wing, which we call the T-shaped proportion of the building, the lower base, and then a podium above grade. So we had backstay issues, we had major transfer. It invokes a lot of comments that were made earlier about proper modeling of your diaphragm for transfer of forces and relative stiffness of your diaphragm versus your vertical system. The aspect ratio, when you look at the steel plate, and I'm just giving you a broad, and then I'm going to come back to the specifics. When you take a steel plate, it's normally the depth of a core, which is roughly 30 feet. But then the aspect ratio, the height is 660, your aspect ratio is over 20:1. So we had to invoke an outrigger system, and that's what you see, a sample of the outrigger at the top of the building, and also another one at the mid-height, not necessarily mid-height, where you have the roof deck over the expanded T-shape or T-wing. The other issue we faced is the transitional floors. And instead of building cantilevers here that were almost 10 to 12 feet, we really developed the concept of a sloping column and cantilevering the floor rather than transferring all these floors. And I can't get the pointer to work here. Here it is. Instead of dealing with this whole cantilever collectively, where the face of the building is here, we basically developed the sloping column, you see that in the diagram, to help transition the floors. The other aspect was, as I think others have hinted, when you have different core configuration, in this by design originally it had different core, which kind of made it challenging for the concrete. Normally in concrete you want to form a spine, and you have the concrete forming, jacking systems that gives it the cost benefits. Here was the distribution of cores because of the many programs and the privacy of the programs and the access that's needed in elevators and stairs and multiple height spaces in between and sky lobby. We ended up with an elevator core all the way on the right side, a middle core, a distributed core here for different aspects, stair exiting. And we took the original concept, we showed them if you do concrete, here is what your distribution of walls is going to be because of the different heights of the different wings. But if we can take that to a lighter system, we basically show them a replica of the location of the concrete walls into steel plates. And the beauty of it being steel plates known to be around 3/8 of an inch versus a 36-inch concrete core walls. So that was, it took a lot of convincing and a lot of background to bring and a lot of skepticism from the developer to the architect to building official. I mean, how can we pull that through? Even the general contractors about pricing the risk basically. Now, this distribution helped us tremendously control and tune the stiffness of the wings and prevent torsional behavior. And then the next issue we'll talk later in more detail about the transition from the high tower to the low tower and what it took extensive analysis and a lot of assistance from the peer review. Now, here is, in summary, after 6 months of time and preparing both concepts, concrete and steel, it became clear to the development and contractor that there is a clear benefit in schedule and in real cost, and also efficiency of the floor plate, because reducing the amount of leasable or rentable or sellable space by having a thin plate system. It's basically an integration of a first order fit between program and structural system. And that's coherent, that maximizes program efficiency. I need to get that out.
Click out of the box.
Okay. Out of the box. Okay. Here we go. Inspired by the lightness of the architectural design and the curvature and the ability to do a flexible form shape, and that really was inspiring some of the ideas of that steel has a little more flexibility to be shaped accordingly. The continuity of the vertical cores being so thin compared to 36-inch concrete walls, the yielding mechanism of the thin plates is integrated with the BRB system in the outrigger, and how in the critical locations providing optimum building response for wind and earthquakes. We're going to get to wind later. This is a quick summary, and my apology, I think somebody in my office shifted a diagram on me. When this, you see the top outrigger configuration at the top of the building. What's represented at the base here is still the top outrigger in the longitudinal direction. They pointed it to the mid-rise outrigger. That's a mistake in the slide. We'll correct that and reissue. I just noticed it a couple of minutes ago. Now, basically, what is the steel plate? It's basically a 1/4 inch throughout the height, except at the transfer at the base where it becomes 3/8 because it's not balancing between the upper and the lower demands. I keep hitting this. Okay, and it basically it's kind of an infill to a frame, what's called the vertical boundary element and horizontal boundary element, and how the system qualifies to some of the aspects of performance required for a dual system. The boundary elements are designed to allow the web plates to develop significant diagonal tension. It's interesting the difference between the concrete shear wall that does not attain its complete yielding. You're going to see here how the yielding starts at a very early phase and how it propagates through considerable height of the steel plate system. And they reach their expected yield stress across the entire panel to dissipate the seismic energy. Here is just a sample of, this is in the middle, you see the floor plate, and in this purple is basically this elevation here, which is in what we call the transverse direction. This is, I can get the mouse to move. Okay. What you see in the pink on the lower plan diagram is location of this configuration of the wall profile. And notice the coupling with the beams, with the floor beams, and the mid-height outrigger and the top outrigger. This is a more detailed, and it gets to what is the outrigger contributing? It's intended to be for drift control. It's improved the system aspect ratio. It's size governed by wind with ALI, especially the outrigger system is strain-based overstrength, capacity protected elements, what was mentioned in several presentations, especially with Greg, that to allow the BRB to perform in a nonlinear and be able to track the demands, we had to protect, all the other elements to remain essentially elastic. And it was included in the nonlinear model. Let me take you back to the background where we kind of collected together. The steel plate shear walls have been around us, and there was a document by a book actually published by Frederick Bleich, and it was mostly used for battleships, where it's a stiffened plate system. Okay, I can get the next slide. and I had a little bit of background in prior practice, where back in the mid-70s, we had to do the Hyatt Regency Dallas in Seattle, and basically it had a lot of guest rooms, but it wanted to be open below the 3rd floor to allow a large meeting room and convention center. So we had basically resorted to a steel plate system between, in partition walls between guest rooms, and being lighter and not concrete, it was much easier to do the transfer. So we transferred the steel plate with open brace frames below grade. But that was the old approach, sorry guys, of what's called the stiff, thick steel plate approach. That's basically had the analogy coming from the plate girder analogy, and its limit state was out-of-plane buckling. The minute we've seen out-of-plane buckling, it requires a lot of stiffeners. It's like the web of a plate girder. Later, a few years after, we had to rebuild the olive view that collapsed in the 71 Sylmar earthquake, and nobody had confidence in redoing this building in concrete, so ended up doing it in steel plates on the exterior of the building. And you see the image of the exterior, and basically it was a battleship with openings and a lot of stiffeners. And the average plate thickness between 1.5 inch to 2 inches in those days was a lot of stiffeners, because the limit state was out-of-plane buckling of the plates. Interesting, I'm giving you a timeline from design of battleships with different plates into the developments in the 80s, mostly done by Jeff Kulak and Robert Driver in Alberta, Canada, of realizing how the research have shown the benefits of post-buckling strength of what's called the selected or thin plate shear wall systems. And it started to show a stable hysteresis loop with some pinching, but it eventually evolved into what is called now the thin plates. So, and there is testing, analytical models. Investigations kept on developing into unstiffened steel plate wall behavior, and development of analysis models, which we call the strip elements representing the unstiffened plates. And test results were shown excellent ductility, resistance to degradation under cyclic loading, high initial stiffness, especially initial shear stiffness, and at the base, inherent redundancy with a moment-resisting frame column connections, distributed yielding and energy dissipation over a considerable part of the height of the building. That's a follow-up test in the 90s, and that kind of confirmed the tension field behavior and the out-of-plane buckling as an energy release rather than a limit state. Tension field led to the light and thin plate concepts. I skipped considerably because we had to reduce this. We had a lot of data on the development of all kinds of analytical tools, actual testing, component testing, or panel testing, or multi-story actually evaluations. And you see that in the material that you have. The interesting part is we were asked to do, or we thought of this concept in 2005, actually late 2004, 2005, and many of the documents, that's why I give you the timeline, we were between the 2001 and the 2007 CBC or 4. It was a period where we had to pick up on what we known to be ongoing research. And that's why we labeled our presentation as kind of from research to practice, which was well supported by the ability to do a performance-based approach with the city. This is kind of, and you've seen some of these documents, but the one that was of best support for us at the time is the Steel Guide 20, which is done by Rafael Sibeli and the team. And at that time, we had access to the draft document and had conversations with Rafael, but that was most what we had. The ASCE 341 was still in development, and that was published later. Our design was kind of in between in the 05 before getting the 2007 CBC. Now, in quick summary, basically, the stiffened shear wall is thick infill plates stiffened to preclude shear buckling versus the unstiffened is no compression capacity. Yes, no compression capacity it has no it's not assigned compression capacity of the thin infill plate. Shear buckling is prevented in the stiffened one. Here, shear buckling of the infill is allowed. And the limited field tension field here is predominantly tension field. Reduced energy dissipation, that's why it was assigned an R of 3, versus eventually the system got assigned an R of 7, and if you put it in a dual system, you can even use an R of 8. And no height limit, we're going to see that later. The AST 360 finally recognized it, and we have the current document, and later, at the time, the 34105, chapter 17, was called the special plate shear wall. And this is the image, just a diagrammatic image of the two types. This is the true behavior. And it starts with, start with the upper left diagram, where basically once you have started drift, or the building drifting, and interstory drift, you initiate buckling of the plate at a very early stage. The minute you initiate buckling, it engages, the plate buckles in one direction, but that invokes a tension yielding of the plate in the other direction, which kind of mobilizes the frame action and so on. Once the frame action is mobilized, the cycle picks up again buckling of the plate in the other direction. And then that leads to development of the tension yield in the strips in the reverse direction, and then that invokes the frame action, and it's a continuous cycle. And the research have shown the benefits of that post-buckling strength that's still available, and we'll see further on that. It's a pinch hysteresis because of some of the frame action and plate yielding. These documents were kind of a gathering of what was around. And actually, many of it, and Jack had mentioned ATC 72 and also San Francisco AB 083. Also, there was a side document that was developed under peer about the expected seismic performance objective of tall buildings, where there was a debate about this occupancy values, enhanced performance, what is expected. And also the LA document, which we had the 2005, but the first document that was around us came around 2008. In brief, you've seen some of this, but this may be a little tuned to the criteria at the time in 2005, 2006, basically to achieve a level of safety at least equivalent to code-based procedure. This was developed by the team. I'm not going to say the engineers of record, but also the peer review. What are we about to engage on, deliver for the city? That was to use the rational alternative process with global criteria equivalency. That's explicit determination of structure performance as best as we can model it. And you've heard a lot of limited knowledge that we still have to assure ourselves of the accuracy of the expected performance. Does not completely disregard code-based guidelines. And then there were all these items from 1 to 9 on standards for code-based versus performance. We had to develop this document to discuss it with the city. Ductility factors, as I mentioned, the R of 8, and the next one, drift limits, which as long as you represent your P delta effects in your modeling and you capture it properly with all the proper techniques of modeling, then it gives you the exemption from the code limits. And similarly, minimum base shear. As much as at the end we ended up designing for a 2.5% minimum base shear. It was more of an insurance and kind of confidence and comfort that we all had between the peer review and ourselves as engineers. Story force distribution, which is the issue of the proper distribution versus accidental mass displacement. 5% eccentricities. Redundancy factor. Okay, we ended up using calculated code values for redundancy only for the DBE. And redundancy factor, importance factor, structural irregularities, structural system, all of this start to show what would be the comparisons between code and performance-based. You've seen some of that in prior presentation. At that time was still the debate about serviceability level and immediate occupancy at that level, rare rare GBE type earthquake 475, and also very rare event, the 2475. We had to deliver to these performance objectives, and the procedure that was used, the analysis type and modeling, and the modeling techniques that pertinent to this system and its configuration and its components and the available sources. In short, the component performance, again, you've heard this morning about displacement-based elements and how do you plan this into your model so you are able to track it, okay? And that's the challenge of how accurate and fully developed your model to meet the expectation at the end result, so you're not disappointed after you do the nonlinear analysis. The steel plate panels are definitely displacement-based element allowed to yield. The horizontal boundary elements, the base of the shear wall, vertical boundary elements only at the base, the buckling restraint brace frames to allow to participate in the inelastic behavior, and the shear links over wall penetrations, and the Verendale outrigger moment connections that were part of the outrigger. The structural elements designed to remain essentially elastic are the force-based, which are your VBE above the shear base, the shear wall base, the local boundary elements. Local boundary elements, you've seen them in the diagram when we had to put doors between two units, secondary local boundary elements, not the main primary vertical column of the entire grid of the building. And gravity and outrigger columns, diaphragms, as much as we had to do some flexible diaphragm modeling to show the transfer, proper transfer, basement walls, mat foundation. On the mat foundation, we use the spring system in the elastic model only, but not in the inelastic. The outrigger steel components beyond the BRB. I'll try to move on. Examples of rationally verified deviations from code. And you've heard about the phi factors. The omega factor, except for collectors. The height limit, the first thing was the height limit that we were allowed to build this for. Per structural system do not apply. The phi factor for the frequent 443 event and the 2475 event, however, we calculated the true phi factor for the 475. On the side note, we did a lot of upper-lower bounding and sensitivity analysis on many issues, on many components also, as part of the concerns being kind of the first of its kind system and configuration. Minimum base shear formula do not apply, as much as I said we use the V minimum eventually of 2.5%. Period limits do not apply. LA Building Code drift, the formula that was presented earlier this morning, I think it was by Jack, that they gave us exemption for. However, we limited, the drift was limited to 3% at MCE. The aspect ratio of the shear wall panels may exceed the maximum. I'm talking about the panel itself. There was code limits about 2.5% of the panel aspect ratio, and due to overall slender wall flexural behavior verified by the nonlinear analysis as recommended by AISC 341, we were given exemptions from that, or we took exception. This is kind of the streamlined process of peer review, or how you first come to agreements with your basis of design, including representation of ground motions, and John spoke about the characterization of the ground motion and the proper inputting in the model and all the uncertainties associated with it. And then you basically can jump to look at, let's follow this one, it's easier. You perform your serviceability level, which in many cases kind of establish more or less close to your final design of your elements. So you have a system that you can check, and it's done with linear elastic modeling, linear elastic analysis, and post-processors. Okay. Then you run your GBE, and we checked it linear elastically also, and made sure that the components satisfy and we're satisfying the code exemption. Then you basically validate your desired or expected or conceived performance and behavior in linear and nonlinear domain by being verified in the MCE analysis of the 2475-year earthquake. This is just a sample of collaboration not only on the evolution of the steel plate design or development of the system itself, but just looking at a portion of the building. If you look at the top, or different, the steel plates, which is in purple, is the test. The latest test was done by Robert Driver, and we use that for a backbone for our analysis. And you'll see later how we try to adhere as close to we can to the test results data. When it came to the link beam outside of the panels, because we also had openings next to the columns sometime, and we had link beams or link beams in between panels, we used the latest Michael Engelhardt at the University of Texas, Austin, for the WOOF-W connection, that he was doing the testing for link beams. We used here from the University of Washington, Charles Roeder tests on composite columns, because some of the columns, the box columns in the corner at the intersect, we needed to develop the composite action grouted concrete columns. Even, which I'm sure you've seen this before, the BRB test in the outrigger was done by Star Seismic, because that was the first one where we needed 2,200 kips load in the BRB element, which was composed of 4 elements. As a side note, I skipped a little bit on ground motion from prior because I knew it was being covered by different presentations. It was done by Geopentech, but to get to the wind, because of the aspect ratio of the building, it became, and also the type of occupancy at the top of the building, the wind became a concern. We engaged in a regional climatic studies and found that we can have a reduction from the wind code almost 25 to 30%, which helped us validate the seismic system for the wind performance. We didn't have to penalize it, especially at the top of the building. And the basis of this is the current prevailing winds that's in many models, or that's the basis of the code, is based on the Santa Ana wind effect, which is most of the measurements are at the airport at LAX, and that's considerably lower horizontally and east-west from the site. By engaging in a regional climatic studies with CPP, we're able to get that reduction. I need to get moving. Then we get into from research testing to calibration of models, and the entire model tried to use the published data from recent documents. Here it gets into the modeling of the diagonal strips into many components, and it following the AIC 341. This is the key thing here. You see the yellow, which is initial yielding. The red is considerable yielding. How the system really has very high usability in the nonlinear domain. We also tracked the tension strips yielding, and you see the great usability usage, and the beam rotations where we're almost at 0.04. In some elements we had a limit of 0.05. The vertical elements usage, which is basically allowed the maximum, the interstory drift, and you see the pinching in the drift at the transition of the floors. This is the interstory drift representing all the ground motions, and the heavy red line is the mean, and then the heavy docked red line next to it is the mean plus 1 sigma. Story shears, the same. And then the transition or transfer of inertia forces. When we originally had a rigid diaphragm model at the top deck here and the pool deck, you'll see the diagrams. Here is the transition at the 27th floor, which became the roof deck. And this is the moment, some of the very strong aspects that Jack has spoke about, and also Greg, about you have moments and you have excessive shears. And interestingly enough, when the red here was showing when we had a rigid diaphragm, and the blue is started showing when we picked up three levels, 25, 26, and 27, and properly modeled them with the relative stiffness compared to this wall system. As a semi-rigid, it starts to dissipate, to distribute the force. When we modeled more flexible floors down to 20 to 28, or from 17 to 28, the transfer became more realistic, more manageable, and then we also did at the base the backstay analysis. Connections and other requirements, there is nothing really peculiar here because of the limited time, but it gives you reference to all the materials and the standards that we were using at the time. Efficiency, benefits, it's a highly energy dissipating system that taller buildings get benefit of shear stiffness at the base and frame stiffness at the top. You get the proper combination of a dual system that's probably properly measured. It's got only 1/4 of an inch. It's got reduced mass by about 25 to 30% and fast track construction. There is new developments that allow you more improvements based on recent test data after we complete it. And the benefits of performance-based design is it expands the limits of things that could have been done and what was able to be accomplished under this project. But it takes a collaboration, and I really mean it. Without the industry, without the peer review, without the code agent, without research across the country, we could owner, contractor, architects to really lead to successful. I have just a few slides on the construction aspects of it. And the collaboration is essential. This is from Herrick, the steel industry, being partners in where you're going to acquire the plates, what's available, cost, how you're going to configure your box columns, the grouted box columns, and holes to allow for the grouting of the concrete, inspection. You will see it. This is the holes that was allowed in the continuity diaphragm to allow the grouting of the columns, to create the composite effects. I mean, it's very essential. Otherwise, you're designing a system that's, and John Hooper touched upon the initial concept of the single core was a genesis of good structural engineering, but architectural needs, programmatic needs, contractors, methods of building. All of this comes to play to better serve these buildings and gives us an opportunity to be able to enhance performance-based engineering to a greater understanding and actually being accomplished. Okay, this is showing conditions in the field, the vertical boundary element anchorage in the mat, and here is the BRB, which is 2,200 kips in 4 pieces, and they actually test, that was the first test that allowed that magnitude of capacity. This is important because the image on the right, it shows you kind of the beam, the starting beam that starts the plate. We had no shear walls discontinuities, but we had columns discontinuities. And I'll show you that later. And how we developed the base connection and how we dialed it into the mat, and also had the startup first component of the plate above so they can be welded, the next tier of it can be welded to it. This is a major transfer beam just above the mat for the column transitions. This is how it came assembled. There were several variations, and you see that on the diagram to the left about how the beam, this is one of what's called the secondary vertical boundary elements, and kind of you see the shear yielding link almost with all the stiffness on top of the opening. And you see how they were able to assemble a lower piece and an upper piece attached to the steel beam, and that's how some of it was erected. This is when we start the transition of the sloping columns. And this is, you see the kind of access holes to allow the splicing of the columns and the inspection. diagonal column. This is the roof system outrigger and the connection of the BRB. And the key important here is it took us almost 05 and 06 to design it and got permitted and peer reviewed through 07 and pricing and so on and shoring, but it did not take them except placement of the mat was November 07 and topping of the building was December 08 to do 55 floors and 3 basements. And that was a big contributing factor for the decision. The goals were enhanced and confirmed performance through performance-based approach and compromise architectural vision, no deep spandrel, as John have mentioned, at perimeter, more sellable floor plate for ownership, and lighter building overall by about 30%, reduced foundation. We actually had a limited, because we were limited by properties adjacent for the entire site. The mat foundation was barely making it for the weight of the building. I mean, if we had heavier system, we would have needed additional supplement for control of settlement under the mat and concentrated pressure under the tower. Early completion of structural frame, they were able to erect 3 floors per week and met the schedule because the schedule was falling behind by early designs. Thank you all. I'm on time, I hope.